All right, so get ready because today we are going deep on a paper that has people talking in the search and information retrieval world. It's called Drowning in Documents: Consequences of Scaling Reranker Inference.
Oh, yeah.
And this is something that you, especially if you are an AI engineer or researcher, you are going to want to know about.
It's a fascinating one. Yeah, I mean, it really kind of gets at some of the assumptions that we often have in AI, right? Like, more data is always better.
Right.
But this paper really challenges that when it comes to re-rankers.
Okay, so let's back up for a second because for those of us who haven't been, just constantly thinking about re-rankers, what are they?
Yeah.
Why are they so important?
So think about it this way. You go to your favorite search engine, you type in a query. The first step is some kind of retriever that goes and sifts through, a massive amount of data
Right.
and tries to find the top, however many documents, could be 1,000, could be 10,000.
Right.
So that's usually done with some simpler method like keyword matching or something like that.
Right.
But then the re-ranker comes in, and that's usually like a more sophisticated model. A lot of times people will use like a cross-encoder.
Okay.
And it takes that smaller set of documents and it tries to rescore them. So it's really trying to improve the accuracy, trying to weed out any false positives, trying to boost the things that are truly relevant.
Okay, so it's like that second layer of like quality control to make sure you're getting the best of the best.
Exactly, yeah.
But this paper is saying that when we scale those re-rankers up, when we give them more documents to score, it doesn't necessarily do what we think it's going to do.
Yeah, that's the surprising thing, right? We would think that as we give it more data to work with, it should get better and better.
Right.
But what they actually find is that at some point, the performance starts to decrease.
So more data, worse results.
Yeah.
That doesn't seem very intuitive.
No.
So what was the actual setup of this research? Like, what were they looking at?
Yeah, so, they had a pretty diverse setup. So they looked at a bunch of different re-rankers. Some of them were open source, some of them were proprietary. And then they also ran it on a bunch of different data sets. What's really interesting is they had both, academic data sets, and then they also had some data sets from like real world enterprise settings.
Oh, that's smart. So they're like covering more realistic search situations in a way.
Yeah, exactly. They want to see like how well does this generalize to like, not just these kind of curated benchmark data sets.
Yeah.
And so, yeah, they looked at a bunch of different data sets. So like, scientific literature, like financial documents. They even looked at some of the like internal technical documentation at Databricks.
Oh, wow.
Yeah, so there's a data set called Finance Bench. It has like questions that come from SEC filings.
Interesting.
There's a data set called Manufacturing QA, which is all about like all the codes that they use in manufacturing.
Okay.
So yeah, there was a pretty wide variety.
That's really cool. So we've got this like really cool set of re-rankers, a bunch of different data sets. How did they go about actually testing this idea of like scaling? Did they just keep throwing more documents at the re-rankers and seeing what happened?
Yeah, so they had to do some like special things just to keep everything like fair and controlled, right?
Right.
So one thing they did is they truncated all the queries and the documents to be 512 tokens.
Okay.
Which is pretty standard for like a lot of these models.
Yeah.
They also downsampled the negative documents to a max of 10,000. Just because, otherwise it would get too computationally expensive.
Right.
But yeah, they were careful to make sure that like even with these constraints, the trends that they were observing were still like consistent.
Okay. So they're trying to create like a fair playing field, basically. So once they did all that and they started increasing the number of documents, what did they actually see? Like what happened?
Yeah, so I mean, it's pretty stark when you look at the figures in the paper, like figure 3 and 4. You see that, at a small number of documents, like less than 100 or so, the re-rankers do what they're supposed to do.
Right.
They improve upon the initial retrieval, but then as you start to increase the number of documents.
Yeah, take a look. I mean, that recall really just plummets. Like, it's like they just get lost in the sea of information.
Right. And that pattern held true across different types of re-rankers, different retrieval methods. So whether they used like a dense retriever, which uses like embeddings, or whether they use something simpler like BM25, which is like a lexical matching method, they saw this consistent trend where as you increase the number of documents, the recall went down.
So it's not just like a problem with one particular type of re-ranker. It seems to be a little more fundamental than that.
Yeah, and that's what makes this research, I think, really interesting, right? It's really challenging this assumption that, bigger is always better when it comes to re-rankers. And then they took it even a step further, which is they said, okay, well, what if we let the re-ranker actually score the entire data set, not just a subset?
Yeah, it seems like it would have like all the information it would need to make a perfect decision, right?
You would think, right? Like it has everything. It should be able to do a really good job.
Right.
But actually what they find is that a lot of times the re-rankers actually perform worse than the simpler retrievers.
That's wild. So, like, they're drowning in data, basically. That's the problem.
That seems to be the problem.
Huh?
Yeah, and the paper doesn't provide a definitive answer as to why this is happening.
Okay.
But they have some pretty interesting hypotheses.
Okay, well, let's hear those hypotheses, because I'm definitely, like, intrigued now.
Yeah.
But before we do, can we just see this in action? Like, are there any really, like, egregious examples where these re-rankers make, like, completely just really weird choices?
Oh, yeah. There's some head scratchers in there. So one example, they have this in Figure 6. The query is about lysine acetylation, which is this very specific biological process.
Okay.
And so even the retriever, which, is using this more basic approach, was able to identify, a relevant document about this.
Okay, so far so good. Like, it's doing what it should be doing.
Right.
What about the re-ranker?
Yeah, so the re-ranker, instead of, recognizing that, oh, this is obviously relevant, it actually buries it way down in the list. Yeah. So it ranked it like 39th.
Wow.
And instead, what it chose to rank higher was this document about something completely different. This thing called like anaphase bridges, which is like this, I think it's a cell division thing.
So think something about cell division is more related to a specific biochemical process.
I know, right? And then it gets even weirder. So in Figure 7, they have this query about this medical condition called Schimmelpenning-Feuerstein-Mims syndrome.
Wow, that's a mouthful.
Yeah. And the relevant document is like a study about this in Gabonese children. The re-ranker completely ignores that and instead thinks that this document about dishwashing is a better fit.
Dishwashing? Are you kidding me? It's like picking the most unrelated thing possible.
I know. And the thing is, unlike BM25, which you can kind of understand, oh, it's doing keyword matching, with these re-rankers, it's like, what is it actually doing? Like, it's hard to really get inside its head and figure out, like, why is it making these decisions? They can seem very arbitrary.
Right. So that leads to the question of why is this happening? Why are these re-rankers drowning? Why are they making these weird choices when we give them too much data?
Yeah, that's the million-dollar question. So the paper puts forward 3 main hypotheses, and they're all pretty, like, thought-provoking.
Okay, yeah, I'm ready to like dive into these because this is fascinating.
Yeah, so the first one they call Hypothesis 1, starved of negatives. So the idea here is that, maybe these re-rankers just aren't trained on enough diverse negative examples. And so if you think about like the embedding models that people use in the retrieval stage,
right?
Those are often trained on like millions and millions of negatives.
Okay.
And so they get really good at understanding, like, what does it mean for a document to be not relevant?
Yeah, they've seen it all at that point, basically.
Right, exactly. Whereas these re-rankers, maybe they're like living in a little bit of a bubble and they haven't really been exposed to that wide range of like bad documents.
They haven't seen the dark side of the internet yet.
Right, exactly.
Okay.
And so, maybe that's why they get so easily distracted by things that are only tangentially related to the query.
Okay, so it's all about that like diverse set of negatives in the training data.
Yeah.
Okay, what about hypothesis 2?
So hypothesis 2 is the ensembling illusion. This one gets a little bit more nuanced.
Okay.
So, we have to remember that these re-rankers are usually used in conjunction with a retriever.
Right.
Right, so they're kind of like refining the results of the retriever.
They're working as a team.
Right, and so what if these re-rankers are actually really good at making like very fine-grained distinctions within like a small pre-filtered set of documents?
Okay.
But when you give them like this massive pool of documents, they lose their advantage.
So it's like they're really good at picking the best apple out of like a small basket of like, carefully selected apples.
Right.
But then when you like take them to an orchard.
Yeah.
And it's just like apples everywhere and pears and all sorts of fruit, they just like don't know what to do.
Exactly.
Yeah.
Yeah, and so this idea like ties into this concept of diversity in ensembles, right?
Okay.
So an ensemble is just like a group of models that are working together, and ideally you want like a lot of diversity in your ensemble.
Right, so that they're not all making the same mistakes, basically.
Basically, yeah. You want them to be like looking at the problem from different angles. And so if your re-ranker is like only good at making these like fine-grained distinctions within this like limited set of documents, then, when you scale up the data, it's not really adding much diversity to the ensemble.
It's not bringing anything unique to the table anymore.
Exactly. And so that might be why we see this performance degradation in the full data set retrieval setting.
Okay, so we've got like the negatives, we've got the ensembling like illusion.
Yeah.
What about hypothesis 3?
So hypothesis 3 is deep learning's Achilles heel, which is this idea that, deep learning models, as powerful as they are,
Right.
they're known to be susceptible to noise and adversarial examples.
Right, like you can tweak those inputs just a little bit and totally mess them up.
Exactly, yeah. And so the idea here is that as you increase the number of documents, you're just exposing the re-ranker to more noise, more irrelevant information, and potentially even more adversarial examples.
It's like trying to find a needle in a haystack, but like every time the more hay you add, the harder it gets.
Right.
Especially if some of that hay is actually like designed to look like a needle, but it's not.
Right, exactly.
Like it's trying to trick you.
Exactly.
Right.
And so that could be another reason why we see this performance degradation.
Okay, this is like kind of disheartening, right? Because we're so excited about re-rankers. Is there like any way to get around this?
Yeah, so the paper actually does offer, I think, a glimmer of hope.
Okay, good. I was getting worried there for a second.
Yeah, so they looked at this alternative approach, which is to use large language models, or LLMs, for re-ranking.
Oh, okay. So LLMs to the rescue. Now we're talking.
Yeah, so instead of using like your traditional cross-encoder, they experimented with using LLMs for what's called list-wise re-ranking.
List-wise re-ranking, what is that?
Yeah, so it's a different way of like framing the ranking problem. So in like traditional re-ranking, like we've been talking about, where you have these cross-encoders, the model is scoring each document like independently, without really considering its position relative to the other documents in the list.
So like each document is like a contestant in a talent show.
Right.
And the judges are just watching each one individually and giving them a score.
Exactly.
They're not like comparing them head to head.
Exactly, yeah.
Okay.
But with list-wise re-ranking, we change the game. We give the model the entire list of documents all at once. We say, hey, rank these.
Okay.
So it's like the judges are now watching all the acts perform.
Okay.
And then they have to decide, like, okay, who's first place, who's second place, all the way down the list.
Okay, that makes sense. So where do the LLMs come in?
Yeah, so the idea is that, LLMs are really good at handling these complex language tasks.
Right.
They can consider context in a very sophisticated way.
Yeah.
And so maybe we can leverage that for re-ranking.
Okay, so do they just like feed the whole list of documents to the LLM and say, rank these?
So not quite. I mean, even LLMs have limits on how much text they can process at once.
Right.
So they had to use this like clever technique where they like used a sliding window.
A sliding window?
Yeah, so imagine you have this really long line of documents.
Okay.
And you create a window that can only see like a certain number of documents at a time.
Okay.
And then you slide that window along the line of documents.
Okay.
And so for each window, you feed those documents to the LLM and you say, hey, rank these.
Interesting. So it's like breaking down that really big ranking problem into these smaller, like more manageable chunks.
Exactly. And one interesting thing they did is they actually chose to start the window with the least relevant documents according to the initial retriever.
Oh, that's interesting. I wonder why they did that.
Yeah, they don't explicitly say why in the paper, but I'm guessing it's probably because they want to like quickly identify and dismiss those really irrelevant documents and then let the LLM focus its energy on like the more challenging cases where the distinctions are more subtle.
So like, don't waste the LLM's time on the easy stuff. Like, let it really think hard about the tough decisions.
Exactly.
Okay, so did this actually work? Like, did this LLM approach actually outperform those traditional re-rankers?
Yeah, so if you look at figure 8 in the paper, what you see is that this list-wise LLM approach, they used a model called GPT-4 Mini. it consistently outperforms the cross-encoder re-rankers across most of the data sets.
Wow. And it seems like the performance is a lot more stable as you increase the number of documents too.
Right. It's not like freaking out and making those weird choices that we saw before.
Yeah. So are LLMs like the solution then? Should we all just like ditch our cross-encoders and just switch to LLMs?
Well, I mean, as with most things in AI, there are caveats.
Right.
So LLMs are computationally expensive to run, especially at the scale that you would need for like real world search.
Right. That's always the trade-off. Like how good is it versus how like practical is it to actually use?
Exactly. But, even if we can't immediately deploy LLMs as our primary re-rankers in every situation, I think their success in this experiment opens up some really exciting new avenues for research.
Okay. Like what?
So one thing we could do is we could use LLMs to train better re-rankers.
Okay. So like use the LLM as like the teacher
Right.
to train these smaller models.
Exactly. Yeah. Like knowledge transfer from the LLM to like a smaller model.
Interesting.
Okay. We could also think about like, the success of the LLMs. Maybe that tells us something about like the architecture of re-rankers. Like maybe we need to move away from this traditional like point-wise approach
Okay.
and explore more list-wise or like hybrid approaches.
So this paper is kind of like a wake-up call, right? It's like,
Yeah.
hey, we need to rethink how we're doing re-ranking.
I think so. Yeah. I think it's a really important contribution to the field.
So, I mean, this has some pretty big implications if you're actually building these systems, right?
Yeah, for sure. I mean, if you are an AI engineer or researcher working on search or recommendation systems and you're using re-rankers, which a lot of people are these days,
Right. Yeah.
you really need to be aware of these scalability issues. Like, don't just assume that more data is going to solve all your problems.
Right. It might actually make things worse.
Yeah.
Like, what can we actually do?
Yeah.
What are some, like, concrete steps that we can take as AI engineers to build better re-rankers?
Yeah. So I think first and foremost, we need to be much more rigorous in how we evaluate re-rankers. So don't just test them on these small curated data sets.
Right.
Like really push them to their limits, test them on large, diverse data sets that actually reflect, the messiness of real world search.
Yeah, like what they did in this paper. Like, test on all sorts of crazy stuff. Like, don't just give it the easy problems.
Exactly, yeah. And I think as we're evaluating them, we need to keep those three hypotheses in mind. So, are we really giving our re-rankers enough negative examples during training? Are we falling into this trap of the ensembling illusion? And are we doing enough to, address those inherent weaknesses of deep learning models, right?
Wow.
To, noise and adversarial examples.
It's a rigorous evaluation.
Yeah.
Really thinking critically
Yeah.
about how we're training these things.
Yeah.
What else?
And then, I think this paper makes a really strong case for exploring these alternative approaches, like the list-wise re-ranking with LLMs.
Right.
And, even if LLMs aren't practical for every use case right now because of, the cost and everything,
Yeah.
I think they're an incredibly valuable tool for research.
So use them to like set the bar, basically, like figure out what's possible and then use that to guide the development of the stuff that we can actually like use every day.
Exactly. Yeah. And who knows, maybe as LLMs get cheaper and more efficient, we'll
Right.
be able to use them more and more in practice.
Yeah. This has been a really fascinating deep dive. Like, I feel like I have a whole new perspective on re-rankers and the challenges of building, really intelligent search systems.
Yeah, it's a really thought-provoking paper. I think it's going to have a big impact on the field.
Absolutely. Well, if you want to learn more, definitely check out the full paper.
Yeah, there's a lot of great details in there that we didn't have time to cover.
And as always, let us know what you think. Connect with us on social media. We'd love to hear your thoughts.
Yeah, we love talking about AI, so feel free to reach out.
Awesome. Well, thanks for joining us for this deep dive, and we'll see you next time for another exploration of cutting-edge AI.